Hi, class. Today we're going to look at section 12.2 notes, part 2, which is still exponential functions, but today we're going to look at the applications, so some word problems. All right, so we're going to have two different types of word problems here. We're going to have interest rate word problems and then a population growth problem. The first thing we need to do is look at our formulas, and you don't need to memorize these, just make sure you know how to use them, and you can always refer back to your notes when you're doing your homework. Our simple interest formula is, is A of t equals p times 1 plus r to the t power. And just to define some of these for us, p is our principal amount of money, so the money amount that we start with. R is the interest rate as a decimal. So if it's in a percentage, which it probably will be, you'll need to convert it to a decimal. And then T is time in years. As an assumption, it's always going to be in years unless they tell you specifically that it's T is in some other time amount. Right, our compound interest, so compounding is when you calculate the interest more than once per year. So simple interest is once per year. And this is more than once per year, and it'll tell you how often it'll be compounded. So our formula, A of t equals p times 1 plus, and then it gets a little different, r over n to the nt. And everything's the same except now we have an n in our equation, and n is the number of times per year the interest is compounded. And it'll tell you, we'll look at an example. All right, and then the next one is continuous compound interest. And this one is going to be infinitely many times per year. So it'll tell you in the problem that it's continuous compound interest. This formula is very different. A of t equals p times e to the rt. And e is a number. It's the number 2.718-ish. It keeps going, just like pi is 3.14, but it's really more than that. E is just another number that we're going to have to get used to using. All right, and then, and there's an E button on your calculator, so if you wanted to pause the video and try to find that E button on your calculator, now is a good chance. All right, and then the population formula, when they write it, they usually use an N, E to the RT, but N is just the initial population, and honestly, it's the same exact formula as this one, as p times e to the rt. So I don't care if you use an n or a p or what you do, but population we can think of as growing continuously. So that's why we use our continuous compound growth equation. All right, let's look at our first example. So we have a simple interest example. Helen is opening her first savings account and is depositing $500. So here's our initial amount. Suppose she decides on a bank that offers 6% annual interest to be calculated at the end of each year. So this is once per year, which makes this simple interest. How much is in her account at the end of 5 years? So the pieces we have P is her principal amount, initial deposit of $500. We have R, which is 0.06. So we want to take that 6% and make it a decimal. And then we have T, which is 5 for the end of 5 years. If I make an equation A of T, I would have 500, 1 plus R to the T power. So it would look like this. And then because it says specifically that T is 5, I want to put that in there. So A of 5 is going to be 500 times 1 plus 0.06 to the 5th power. And I want you to get your calculators, pause the video, see if you can type that in your calculator correctly. 500 times 1 plus 0.06 to the 5th power is $669.11. Don't forget your cents. Every penny counts. All right. Example 2, we have a compound interest problem. Suppose the bank now wants to start compounding the interest at the end of each month. They still want to offer 6% annual interest. They still want to look at 5 years. She's still depositing $500. But now N, which is the number of times per year it's compounded, if it's every month, then it's going to be 12 times per year. So using our compound interest formula, we have A of t equals our principal amount, 500, times 1 plus our interest rate, our annual interest rate, 0.06, divided by 12, because it's going to be 6% for the whole year. So every month it's going to be 1/12 of that 6%. And then it's going to happen 12 times 5 times. So 12 times 5 for our exponent, because they're calculating that at the end of every month. So 12 times a year for 5 years. When you plug this in your calculator, don't forget to group the 12 and the 5 together in your exponent. So I want you all to plug this in your calculator to make sure that you're plugging it in correctly. And if you didn't get what I get, try to make sure to put parentheses around the 12 and the 5. So 500 times 1 plus 0.06 divided by 12 to the 12 times 5 power gives us $674.43. So look at that. $669.11 to $674. We made an extra like $5 there. Even though we started with the same amount, we had the same interest rate for the same amount of time, compounding the interest ends up giving you a little bit more money. So go home and look for bank accounts with compound interest. Put your money in there. All right, and then we're going to look at a continuous interest situation. So same bank, same amounts, but this time it's compounded continuously, so infinitely times per year. So we have to use this formula, P e to the RT. We're going to plug in all of our things. So A of 5 years, equals 500 for our principal amount times e to the r, which was 0.06, times 5 for t. So again, make sure that those pieces are grouped together in the exponent. And then you'll find a button on your calculators that looks like e to the x, and you're going to want to use that one. So pause the video, see if you can figure that one out. 500, then the e to the x button, and 0.06 times 5. And we get, $674.93. So from the last one compounded monthly to this one compounded continuously, we gained about 50 cents. So not as big of a jump as simple to the monthly compounded, but it still is a little bit more money. All right, and then our last example here, we're going to do a population growth example. It works similarly, but it's a little different, population instead of money. The population of the city of Fredericksburg, Virginia was approximately 19,360 in the year 2000 and has been continuously growing at a rate of 2.9% each year. So that word right there, that continuous growth, is what tells us that we need to use that PERT equation, or you can use an N instead of a P if you want, in this problem, and really for any population problem unless they tell you otherwise. So use the formula to write a function to model the growth. So when I write my function, I don't know how many years I'm doing it for. So I'm going to use t as the variable. So A of t equals my initial amount, 19,360, times e to the r. And remember, we need to convert our percentages to decimals. So 2.9% is 0.029. 0.029 times t. So there's our function to model this population growth. B, use our function model to predict the population in 2013. So remember, up here it said it was starting in 2000. So how much time has passed? It's been 13 years. So now I'm going to find A of 13 to see what the population might be. 19,360 e to the 0.029 times 13. Again, you can pause your video and see if you can type this into your calculator. 19,360 e to the 0.029 times 13 is 28225 0.027, but it doesn't make any sense to have a decimal value when you're talking about population. So we need to round this to the nearest person because we can't have decimals of people. So don't forget to round. All right, and last one, what does the value, or what value does your function model give for the population in the year 1980? So now we're going to go back in time from 2000 to 1980. That's negative 20 years. It's weird to think about negative time, but that's what's happening. So a of negative 20 equals 19, what was it, 360 times e to the 0.029 times negative 20. If you think about it, we should end up with less people than we had when we started. So less than 19,360. E to the, press the wrong button here. E to the 0.029 times negative 20. And you should end up with 10839.6. So again, we need to round 10840 people. All right, and that's it for our part 2 lesson.